Welcome to TechDaily.ai. So glad you could join us for another deep dive. And this one is really important, essential really for anyone navigating the digital world we live in. Our mission today, we're going to try and untangle some pretty critical ideas. All right, keeping your information safe, whether that data is just sitting there or maybe flying across networks or even being actively used by your apps. We want to cut through the jargon, the complexity of data security, and give you a clearer picture, a roadmap maybe, showing how the big cloud players are handling these challenges and crucially what it all means for you. This deep dive is proudly sponsored by StoneFly. They're your trusted solution provider and advisor in a whole range of areas. We're talking enterprise storage, backup disaster recovery, hyperconverged setups for VMware, Hyper-V, Proxmox clusters, AI servers, also SA365, which is a turnkey security appliance, and they handle both public and private cloud solutions too. You can find out more at stonefly.com. That's stonefly.nr.com. Okay, so to really get a handle on securing our digital world, we first have to understand what exactly we're trying to protect.
Because it's way more than just files on a hard drive, right? Data actually lives in these different states, and each one has its own weaknesses, its own vulnerabilities. And each state demands a specific defense strategy. Let's peel back those layers. Let's see why understanding these states is, well, absolutely foundational.
That's exactly right. Yeah, understanding these states isn't just theory. It's fundamental, foundational, like you said. You can't build a really strong security strategy today without getting this. Right. Because the threats change depending on what the data is doing. We mainly talk about three states: data at rest, data in transit, and the newer one, data in use. Each one. Different challenges, different protection needs, because the risks morph, depending on if the data's sitting still or moving. It's kind of like guarding treasure, right? You need to secure the vault when it's locked away. You need to secure the convoy when it's being transported. And you even need to be careful when you're actively counting the gold coins inside. So first up, let's talk about data at rest. This is data that's stationary. It's dormant, not actively moving around. Think of it like data that's sleeping peacefully, just sitting there. Exactly. On hard drives, laptops, maybe USB sticks, but also in bigger systems, think about data archived in block storage or object storage databases, even all the data piling up on Internet of Things devices, IoT stuff, it's everywhere. Now, here's the thing. It might seem less vulnerable because it's not moving.
Yeah, it seems safer just sitting there.
But attackers, they often see data at rest as a more valuable target.
Really? Why is that?
Because it's concentrated. It's a gold mine, potentially. Think sensitive customer lists, business plans, design documents, health records. If someone gets into that static data, the impact can be huge, catastrophic even. So protecting the sleeping data isn't just like a good idea. It's mandatory. For privacy rules, for compliance regulations, for data sovereignty laws that say data has to stay in certain places, if you don't protect data at rest properly, even something like a physical break-in or someone just getting onto a dormant server, boom, major data exposure. So yeah. It looks passive, but it's a high-value target, needs strong encryption, good access controls, vigilance.
Okay, so it's not just about locking the vault door. It's about making sure the gold inside is somehow protected too, even when it's just sitting there. Makes sense. But like you said, data rarely just stays put in our world, does it? It's always flowing, moving, like a river. And rivers, well, they have their own nature.
They absolutely do, which leads us straight into the second state, data in transit. Or data in motion. This is data that's actively moving from one place to another. Picture it streaming across the internet, or maybe through a private company network, or even just moving between processes inside a single computer, like during an input-output operation. It's data communicating, like a conversation happening, potentially over an open channel.
So emails, file transfers, web browsing, that kind of thing.
Exactly. Transferring data over a public network is a prime example, or moving data between your own data center and the cloud. Think about hybrid connections like Azure Express Route, for example, or even Google Cloud's internal system, ALTS they call it, for their own internal communications, RPC traffic. And yeah, even just data going from your phone to a cloud app, that's data in transit. Now, data is often seen as less secure when it's moving. Why? Because it crosses more points where someone could potentially intercept it.
Right, more opportunities to listen in.
Precisely. Organizations that don't protect data in transit properly are really vulnerable to things like man-in-the-middle attacks.
Ah, yes, where someone gets between you and who you think you're talking to.
Exactly. They secretly relay the communication, maybe even change it, and you wouldn't know. They're also open to simple eavesdropping, just listening in, and session hijacking. Getting control of your communication session can be the first step for an attacker to get into confidential systems. So, good protection for data in transit, usually strong encryption like TLS, is absolutely critical, vital. It's like putting that treasure in an armored car for the journey. You have to secure the transport.
Okay, so data at rest is the gold in the vault. Data in transit is the armored car journey. What about when you actually open the vault, take out the gold, and start using it? When the data is actively being processed, that feels like a different kind of challenge, maybe a blind spot for older security methods.
It is, and it's probably the most cutting-edge area in data security right now. We often talk about it as data in use, or more specifically, under the banner of confidential computing. This is about protecting data when applications or services are actively working on it, processing it, analyzing it. This is where the real work gets done with data, but it's also where these new risks pop up, risks that were kind of overlooked before.
How so? What's the risk there?
Well, traditionally, when data needs to be processed, it gets loaded into the server's memory, right, the RAM. And historically, at that point, it often exists in an unencrypted state, just temporarily while the CPU works on it.
So it's exposed in memory.
Exactly. And that creates a potential blind spot. If an attacker manages to compromise the server, the underlying infrastructure, they could potentially read the server's memory and see that sensitive data while it's being processed. Your secrets laid bare. Confidential computing is designed to solve exactly that problem. It protects data even while it's in the server's memory, which, as you said, was a major gap. How? Through specialized hardware. Think specific chipsets from AMD like SEV or Intel with SGX or TDX. These allow for what are called confidential compute virtual machines, or VMs.
Okay, so special VMs, what do they do differently?
They're designed to keep the data encrypted in memory using keys that are managed entirely by the hardware itself. And here's a really crucial part. The keys used for this memory encryption are often ephemeral.
Ephemeral, meaning temporary.
Yes, generated right there on the chip for that specific processing task. They can't be exported. And critically, even the cloud provider, the people running the infrastructure, cannot access those keys.
Wow. So even the provider can't see the data being processed.
That's the goal. It fundamentally changes the trust model. The benefits are pretty huge. Transformative, really. First, like we just said, it drastically reduces the need to trust the infrastructure provider. Since the data stays encrypted during processing, the provider can't get at it. Which, by the way, can also reduce their liability regarding your private data.
Okay, that's big. What else?
It massively helps organizations meet really strict compliance regulations. Think healthcare data under a HIPAA or financial data. Processing that securely becomes much more feasible, and maybe one of the most exciting things, it enables secure, untrusted collaboration.
Untrusted collaboration. What does that mean?
Imagine different companies, maybe even competitors, wanting to pool their data for analysis without revealing their own sensitive raw data to each other.
Like banks pooling fraud data or hospitals pooling research data.
Exactly. With confidential computing, they could run analysis on the combined encrypted data set. They get the collective insights, but nobody sees anyone else's specific confidential information. It's sometimes called blind processing. It's a massive step in closing the loop, mitigating risks right at the point where data is most active. It completes the trifecta: rest, transit, and now in use.
That really is incredible. Protecting data while it's being worked on, it closes that final major security gap. Okay, so we have these three states: rest, transit, use. We understand the unique risks. So how do we actually do the protecting? The word that always comes up is encryption. But how does encryption actually work? And why are the keys, the things you use to lock and unlock it, so incredibly important? It feels like they're two sides of the same coin.
You've absolutely nailed it. Encryption is fundamental. It's a cornerstone of cybersecurity. You can't really talk about data security without it. At its core, it's pretty simple conceptually. It takes your readable data, your plaintext, and it uses a mathematical recipe, an algorithm, plus a secret ingredient, the key, to transform that plaintext into scrambled nonsense, ciphertext, unreadable without the right key. To get the original information back, you need that exact key to reverse the process, to decrypt it. Without the key, the ciphertext is just digital garbage to anyone unauthorized. Useless. Now, when we talk encryption, there are generally two main flavors we use. First, there's symmetric key encryption.
Symmetric, meaning the same key does both jobs.
Exactly. One single shared secret key locks it, encrypts, and unlocks it, decrypts. A very common and strong standard today is using a 256-bit symmetric key. AES 256 is the algorithm you hear about most often. And here's something really important for the future. The general consensus right now is that 256-bit symmetric encryption is actually secure even against well, against the potential threat of powerful quantum computers.
Oh, wow. So data encrypted like that today is potentially safe even from future quantum code breakers.
That's the current thinking, yes, which is a huge deal. It means generally data at rest that's already encrypted with strong symmetric keys doesn't necessarily need re-encrypting just because of the quantum threat. It offers some peace of mind for existing archives. It's like having a really, really complex combination lock. Same combo opens and closes it. The second type is asymmetric encryption, often called public key encryption.
Asymmetric. So different keys.
Right. This uses a pair of keys that are mathematically linked but different. You have a public key, which you can give out freely to anyone. They use this public key to encrypt messages for you. And then you have a private key, which you must keep absolutely secret. Only you, with your private key, can decrypt messages that were encrypted with your public key.
Ah, okay. Like a mailbox. Anyone can drop a letter in the public slot, but only I have the private key to open the box.
Perfect analogy. This is the foundation for a lot of secure communication online. Think TLS for secure websites, HTTPS, digital signatures to verify documents or software. It lets people communicate securely or verify identity without having to secretly share a single key beforehand. However, and this is a big however we'll definitely come back to, these asymmetric algorithms, these are the ones that are potentially vulnerable to being broken by powerful quantum computers in the future.
Okay, so symmetric seems pretty robust for now, but asymmetric, while essential today, has this looming quantum question mark. Got it.
Exactly. And building on that, regardless of the type, something called key rotation is incredibly important.
Key rotation, meaning changing the keys regularly.
Yes. Generating new encryption keys periodically and starting to use them for new data while phasing out the old ones. Why? It dramatically reduces the impact if a key ever gets compromised. If an attacker gets hold of one key, they can only decrypt the data that was encrypted with that specific key. If you rotate keys often, you limit the amount of data exposed by any single key compromise. It contains the damage, limits the blast radius, as they say.
Right, so one lost key doesn't expose years and years of data.
Precisely. It's a proactive defense. Like changing the locks on your house periodically just in case. Minimizes potential future damage.
So the keys are literally the keys to the kingdom. Encryption scrambles the data, but if you lose the key or someone steals it,
it's game over for that data. The encryption is worthless no matter how fancy the algorithm was.
Which means managing those keys securely must be just as important as the encryption itself. How do we do that, especially in these huge, complex cloud environments? Managing potentially millions of keys must be a nightmare.
You've hit the absolute core principle. Protecting the keys is protecting the data. They are inseparable. And you're right, managing them securely at scale is a massive challenge. That's where dedicated key management solutions, or KMS, come in. These are really the unsung heroes of cloud security. They handle the entire lifecycle of cryptographic keys: generation, secure storage, controlled usage, rotation, auditing, and eventual destruction, all in a secure, manageable way. Trying to build something comparable yourself, it's incredibly difficult and expensive.
So what do these cloud KMS offerings look like? Can you give us some examples?
Sure. Let's start with Microsoft's offering, Azure Key Vault. Key Vault is designed specifically to safeguard keys, but also other secrets like passwords or connection strings used by cloud apps and services. It streamlines key management, but critically, it's designed so that customers retain control over their keys. Microsoft doesn't just hold them for you, you manage the access policies. And importantly, Key Vault is often backed by hardware security modules, or HSMs.
HSMs, you mentioned those. What are they again?
They're basically tamper-resistant physical devices.
Yeah.
Specialized hardware designed only for cryptographic operations. They make it extremely difficult, physically and logically, for anyone to extract the keys stored inside, even if they somehow got access to the server hardware itself. It's like a digital safe for your keys.
Okay, so Key Vault uses these HSMs for extra protection. What are the main benefits of using something like Key Vault?
Several big ones. It centralizes where you store your application secrets, which drastically cuts down the risk of them being accidentally leaked in code or configuration files. It gives you really granular control over who or what can access those keys and secrets. And it logs everything, every access attempt, every use. Great for audits and compliance. Plus, Key Vault can manage the whole lifecycle of your TLS certificates, requesting them, renewing them automatically, takes a big operational headache away.
And for people using it, any best practices?
Definitely. Use Azure's Role-Based Access Control, RBAC, for managing who can administer the Key Vault itself. Then use Key Vault's own access policies to control which applications or users can actually use the keys or secrets stored inside. 2 layers of control. Store important certificates in there, don't leave them lying around on VMs. And crucially, enable the soft delete and purge protection features.
Soft delete, like a recycle bin for keys.
Exactly. It prevents accidental deletion. If you delete a key or vault, it goes into a recoverable state for a set period. Purge protection stops even administrators from permanently deleting it during that window. Absolutely vital, especially for keys encrypting your main data stores. Protects against accidents and malicious insiders.
Okay, that makes sense. What about the other big cloud providers, Google Cloud and AWS?
Very similar concepts. Google Cloud Key Management Service, KMS, also lets customers generate, use, rotate, and destroy their keys based on their own policies. Puts the control in the customer's hands. And AWS Key Management Service, KMS, is another core security service there. AWS has actually been quite proactive in looking ahead. They started integrating proposed algorithms for post-quantum cryptography, PQC, key encapsulation, into their KMS way back in 2019.
Wow, 2019. That's really looking ahead at that quantum threat we talked about.
It is. It shows just how seriously the major providers take key management and future-proofing their platforms. These aren't just key lockers, they're sophisticated cryptographic engines designed for the long haul.
What's really fascinating here is seeing how these huge cloud providers aren't just reacting to today's threats. They're actively weaving these advanced encryption ideas and even preparations for future quantum threats into their massive global operations. The scale of it is just mind-boggling. It's like they're trying to build a quantum-proof digital fortress for everyone's data.
That's a great way to put it. This is really where the theory meets practice, on an immense scale. AWS, Google Cloud, Azure, they've each built these incredibly sophisticated, multi-layered security approaches. It reflects the sheer size and complexity of the cloud. It's not just adding one security feature, it's embedding security deep into the architecture, often achieving a level of resilience that's tough for individual companies to match on their own. Let's dive into AWS first, especially their work on post-quantum cryptography, or PQC. Now that quantum threat, it's serious, even if it's still theoretical today.
Meaning no one's actually built a quantum computer powerful enough to break today's crypto yet.
Correct. No public evidence of one anyway. But if or when one is built, it could shatter the security of current public key algorithms, the ones used for establishing secure connections, for digital signatures, the very foundation of secure online communication. AWS isn't waiting around for that possibility. They're acting now.
Why the urgency if the threat is still maybe years away?
Because migrating critical global infrastructure to new cryptographic standards is a monumental task. It takes years of planning, development, testing, and deployment. Think about replacing every lock on every secure door in the world almost simultaneously. You have to start early. AWS approaches this using their shared responsibility model.
Right. The idea that they secure the cloud infrastructure, but customers secure what they put in the cloud.
Exactly. So for PQC, some features they're rolling out will be enabled automatically, transparently. Customers get a baseline level of quantum-safe protection without doing anything. Other features will be optional, things customers can choose to implement for specific needs, maybe higher security requirements. And AWS has been deep in this space for a long time, involved in the PQC standardization process for about 8 years. That work paid off recently, August 13th, 2024, when NIST, the U.S. National Institute of Standards and Technology, announced the first official PQC standards.
Okay, so official quantum-resistant algorithms are here now.
Yes, 3 key ones initially. ML-Chem, that's Crystal's Kuiper, for establishing keys securely. ML-DSA, Crystal's dilithium for digital signatures. And SLH-DSA, SphinCS plus BlackSci, another signature scheme. These are designed to replace the vulnerable algorithms we use today. And notably, AWS engineers were actually contributors to developing these standards. Shows their deep involvement.
So how are they actually rolling this out? It must be complex.
It is. They have a multi-layered migration plan, several work streams running in parallel. A big focus is encryption in transit. Why? Because that's where vulnerable public key algorithms are heavily used negotiating session keys over insecure networks like the internet. Remember how we said 256-bit symmetric encryption used for data at rest is likely quantum safe?
Right, so they don't need to worry as much about re-encrypting stored data for this specific threat.
Correct. That's a massive relief for everyone with huge data archives. The main immediate action is on securing the connection. So another workstream is implementing hybrid post-quantum key agreement on their public endpoints.
Hybrid, meaning mixing old and new.
Exactly. When you connect to an AWS service over HTTPS, The system will establish the secure session key using both a classical algorithm, like elliptic curve Diffie-Hellman, ECDH, and a new PQC algorithm, like MLChem. The final session key depends on both methods succeeding. So an attacker would need to break both the classical crypto and the quantum-resistant crypto to compromise the connection's confidentiality.
Like a double lock. One traditional, one quantum proof. Raises the bar significantly.
Hugely. It provides security against both current threats and future quantum threats simultaneously. It's a very clever transitional strategy. They're using their own open-source crypto libraries for this, like AWSLC and S2NTLs, and rolling it out across most of their HTTPS-based services, the ones you access via the AWS console, SDK, CLI, plus services like load balancers, API gateway, CloudFront. They're also tackling long-lived roots of trust.
What does that mean?
Think about things that need to stay secure and verifiable for decades, but are hard or impossible to update, like firmware on a satellite or embedded IoT devices. The digital signatures used to validate their software or authenticate them need to be secure against future threats. So AWS is adopting the new PQC signature algorithms, like MLDSA, for these scenarios. They plan to offer this first in AWS KMS, letting customers generate and use PQC keys within their secure HSMs. And finally, they're working on integrating PQC for session-based authentication, like verifying server and client certificates in TLS and SSH. This is trickier. Needs broader industry coordination with certificate authorities and browser makers.
So what's the big takeaway from all this AWS PQC work for someone listening?
The key takeaway is this hybrid approach. It's not just swapping algorithms. It's building a bridge to a quantum-safe future while maintaining security today. It ensures resilience. Even if one method eventually fails, the other should hold. It's a strategic blueprint for long-term digital security. And for customers, AWS advises ensuring you have processes to quickly deploy software updates for their tools like the CLI and SDKs, but also your own apps. And critically, adopt TLS 1.3 across the board as it's required for using PQC effectively.
That's a seriously impressive forward-looking strategy from AWS. Okay, let's pivot. What about Google Cloud? How are they tackling data security and giving customers control, given their massive scale and infrastructure expertise?
Google Cloud also takes a really comprehensive approach, but perhaps with a stronger initial emphasis on security being built in and default, combined with very flexible layers of control for customers who need it. Their philosophy feels like secure by default, highly configurable if needed. For instance, by default, Google Cloud encrypts all customer data when it's stored at rest. They use AES 256 automatically. You don't have to flick a switch, it just happens.
So baseline encryption is just table stakes for them.
Pretty much. Same for data in transit. All their virtual network traffic is encrypted using standard TLS for external connections. And internally, between their own services within their network, they use something called Application Layer Transport Security, or ALTS. It's their own optimized protocol for securing internal RPC calls. So data is protected moving to Google Cloud and within Google Cloud by default. But where Google really offers flexibility is in customer control over encryption keys. This is where those layers come in.
Right, because default is easy,
Right.
but some industries need more direct control.
Exactly. So layer one is that cloud-native encryption, the default. Google generates the keys, Google manages them. Easiest, least control for the customer. Layer two is cloud platform key management. Here, Google still generates the master keys within their KMS, but these master keys are used to encrypt your actual data encryption keys, DEKs. You get a bit more control, you can manage access to the master key, maybe delete it to render data inaccessible, but Google still owns that master key. Layer three is bring your own key. BYOK, this is pretty common. You, the customer, generate your own master key, maybe in your own secure environment, and then you import it into Google's KMS.
So you own the key material originally?
Yes, you retain ownership. If you lose it in the cloud KMS somehow, you can re-import it. You can use the same key across different Google projects or regions. It gives you more assurance. But once imported, Google's KMS still has access to that key to perform decryption for you. Fortanix, for instance, supports BYOK for GCP, AWS, Azure, even Salesforce.
Okay, so still some level of trust in the provider's KMS. What's next?
Next level up is bring your own KMS, BYOKMS. This is where it gets really interesting for high security needs. Here, the master keys are not imported into Google's KMS. They stay outside, managed by an external key management service. Could be on-premises, could be another trusted provider like Fortanix DSM.
So Google systems never actually see the master key itself.
Correct. When Google needs to encrypt or decrypt data, it makes a call out to your external KMS, passing the D, E, and asks the external KMS to wrap unwrap, decrypt it using your master key. The master key never leaves your control boundary. You can revoke access instantly by cutting off the external KMS. Google offers this via their Cloud External Key Manager, Cloud EKM service for supported products. Fortanix also supports this model for GCP and AWS.
That sounds like a significant jump in control in the security. Is there anything even beyond that?
There is, though it's less common due to complexity. It's bring your own encryption, BYOE. Here, you basically do everything. You manage the DKs, you perform the encryption operations yourself, perhaps within your applications running on Google Cloud VMs. Google Cloud essentially just stores opaque blobs of already encrypted data for you.
Maximum control, maximum responsibility.
Exactly. It gives you the highest level of security assurance, very similar to running in your own data center. But it can break integration with some native Google Cloud services that expect to be able to work with the data directly, using keys managed via the other methods. It requires running your own KMS, potentially both in the cloud and on-prem, and managing complex integrations.
So Google offers this whole spectrum, from easy defaults to total customer control. That's impressive flexibility.
It is. And beyond keys, Google is also a major player in confidential computing. Their confidential VMs use AMD SEV technology, similar to what we discussed. Data stays encrypted in memory during processing. Keys are ephemeral, generated on-chip, non-exportable. Google doesn't access them. Their stated goal is unified control across rest, transit, and use. They also have strong access control and transparency features. Cloud IAM for fine-grained permissions. VPC service controls to create network perimeters preventing data leaks, identity-aware proxy, IAP, for context-aware access to apps based on user and device state.
And transparency, you mentioned that earlier.
Yes. Beyond the standard audit logs tracking your users' actions, they have access transparency logs. These log actions taken by Google personnel when they access your data, maybe for a support ticket you filed or during an outage investigation. They even log the justification given.
Wow, logging what the provider does, that's unusual.
It is, and they take it a step further with access approval. This allows you to require explicit approval from you before Google personnel can access your data or configurations for support purposes. It gives customers remarkable oversight. They also focus heavily on data lifecycle and resilience, secure data deletion processes, physical media sanitization. Data is replicated multiple times across servers, zones, regions for high availability. They leverage their huge private network for performance and resilience, and run annual company-wide disaster recovery tests called DIRT to find weaknesses proactively. For data governance, they offer Cloud Data Loss Prevention, DLP, to discover, classify, and de-identify sensitive data using techniques like tokenization or pseudonymization. Data Catalog helps manage metadata, and they support data residency, letting you pin data at rest to specific geographic locations, like the EU, for compliance. Plus, a commitment to open cloud principles tools like Anthos for managing workloads across multiple clouds, support for open source like Kubernetes.
Okay, that's an incredibly deep suite from Google Cloud, especially the transparency and key control options. So, let's complete the picture with Azure. How does Microsoft's cloud platform approach this multifaceted data protection challenge? What are their highlights?
Azure, absolutely. They offer a similarly comprehensive framework deeply integrated across the Microsoft ecosystem, which makes sense given their enterprise software heritage. They definitely cover all the bases for protecting data in its different states. For data at rest, encryption is default in core services like Azure Storage and Azure SQL Database. That's the baseline. For virtual machines, they offer Azure Disk Encryption. This uses standard OS-level tools, BitLocker for Windows, dmcrypt for Linux to provide full volume encryption for the OS disk and any data disks attached to the VM. And crucially, like the others, customers can integrate this with Azure Key Vault to manage the encryption keys themselves. You can use platform-managed keys or manage your own for tighter control.
So, similar options for VM disk encryption and key control. What about data moving around in transit?
For data in transit, Azure's baseline recommendation is always use SLTLS, HTTPS everywhere, essentially. For connecting your on-premises network to Azure, they offer Azure VPN Gateway. This gives you secure, encrypted tunnels either site-to-site for connecting whole networks or point-to-site for individual remote users. If you need higher bandwidth or a more dedicated connection than the public internet, there's ExpressRoute. that provides a private WAN link directly into Azure's network.
Is ExpressRoute itself encrypted?
ExpressRoute provides a private connection, but the encryption of traffic over ExpressRoute is typically handled at the application layer using SSL/TLS, or potentially using EPISEC encryption at layer 2, depending on the configuration. So you still generally layer encryption on top. And naturally, all interactions with the Azure portal itself, especially when managing storage, happen over HTTPS by default. They stress that protecting data in transit is vital to prevent those man-in-the-middle attacks, eavesdropping, session hijacking we talked about.
Makes sense. And for the third state, data in use, confidential computing.
Yes. Azure is also heavily invested in data in use protection via confidential computing. They offer confidential compute VMs based on both AMD SC vSNP and Intel TDX technologies. Just like Google Cloud, these are designed to keep data encrypted in memory while it's being processed, using hardware-managed keys inaccessible to the host environment, including Microsoft operators. It's aimed squarely at protecting sensitive workloads during processing, reducing the need to trust the underlying infrastructure, and enabling those secure multi-party collaboration scenarios. Beyond these core encryption areas, Azure emphasizes a couple of other important practices. One is the use of secure workstations, sometimes called privileged access workstations, PA.
Why focus on the workstation?
Because the endpoint, the admin's or developer's machine, is so often the initial point of compromise and attacks. If that machine is compromised, attackers can steal credentials or hijack sessions to get into cloud resources. So Azure recommends using dedicated, hardened, securely configured workstations specifically for administrative tasks or accessing sensitive data. It dramatically reduces the attack surface associated with privileged operations. It's about securing the human interface point. They also stress enforcing security policies across all devices consuming data, not just servers.
Good point. Secure the admin before they touch the cloud. What else?
Another key piece is Azure Information Protection, or AIP. This is less about infrastructure encryption and more about classifying and protecting the data itself.
Like labeling documents as confidential.
Exactly, but it's much more than just a label. AIP allows you to classify documents and emails, automatically based on content, manually by users, or a mix. These classifications apply labels which can include visual markings, headers, footers, watermarks, but also embed metadata. And crucially, AIP integrates with Azure Rights Management, Azure RMS technology. This applies persistent protection encryption, identity checks, authorization policies directly to the file or email itself.
So the protection travels with the data.
Precisely. Doesn't matter where the file goes, shared outside the company, saved to a USB drive, emailed, the protection stays with it. Only authorized users authenticated via Azure AD can open it, and you can define specific permissions, view only, cannot print, cannot forward, etc. It allows organizations to control their sensitive information even after it leaves their direct control. Usage logging is also available to track who's accessing protected documents. It's a powerful way to extend protection beyond system boundaries right down to the individual data asset.
That's a really comprehensive picture, protecting the infrastructure, the connections, the processing, the admin access points, and even the data itself as it moves around.
Okay, this brings us to some broader strategies. We've hit encryption hard, looked at the cloud providers, but you mentioned other powerful ideas are out there too, like zero trust and this thing called tokenization. These sound like they take things up another notch. How do they fit into this whole security landscape? Are they replacements for encryption or something else?
That's a great question, and it gets to the heart of modern security architecture design. How do we secure things when the old idea of a secure network perimeter just doesn't exist anymore? With cloud, remote work, mobile devices, the perimeter's everywhere and nowhere. That's where zero trust comes in. It's less a specific technology and more a strategic approach to security.
Okay, a strategy. What's the core idea? The mantra is never trust, always verify. It's a security framework that fundamentally rejects the old idea of inherent trust based on network location. It demands strict identity verification for every single user and device trying to access any resource. Doesn't matter if they're inside your old office network or connecting from a coffee shop. Every access request is treated as potentially hostile until proven otherwise.
So no more trusted internal network.
Exactly. That trust but verify model, where being inside the firewall granted you a certain level of trust, is obsolete. Zero trust assumes threats can be anywhere, inside or out. The key concepts are no assumed trust. Everything needs verification. It provides comprehensive security across all environments, local, cloud, hybrid. Ideal for today's scattered workforce and infrastructure, and it demands continuous monitoring and validation. Verification isn't a one-time gate check at login. Trust is assessed dynamically, continuously, throughout the entire session based on real-time signals.
Continuous verification, how does that work?
It relies on gathering context. Is the user logging in from a known device, a typical location, at a normal time? Is the device healthy and patched? Is the user trying to access data appropriate for their role? Based on this dynamic risk assessment, access might be granted, denied, or maybe require an additional authentication step, like MFA. NIST, in their guide 800-207, lays out some core principles for zero trust. First, continuously verify. Like we said, no default trust. Access is based on dynamic risk, adapting quickly to changes, high security without hopefully wrecking the user experience. Second, limit the blast radius. If a breach does happen, minimize the damage. How? Through things like microsegmentation, often based on identity, not just network address, and the principle of least privilege, users and systems only get the absolute minimum permissions needed. This stops attackers moving laterally easily if they compromise one part. Third, automate context collection and response. You need data from everywhere: user credentials, device health, network traffic, data access patterns. Integrate this with your security tools, SIEM, SSO, threat intelligence, to make fast, accurate, often automated decisions and responses. Humans can't keep up otherwise.
What kind of technologies enable this?
It's a combination. Risk-based multi-factor authentication, MFA, is huge. Identity protection systems, next-gen endpoint security, EDR, cloud workload protection platforms, CWPP, strong data encryption, obviously, secure email gateways, verifying device health and compliance. Implementation is usually phased. Visualize your assets and risks. Mitigate the biggest threats first, then optimize protection across everything, the payoff. It's ideal for securing complex environments, multi-cloud, remote workers, legacy systems, SaaS apps. And it directly tackles major threats like ransomware by controlling execution identity, supply chain attacks, better checks on device users, and insider threats. Continuous verification makes malicious internal activity harder to hide. It's really security designed for the modern distributed world.
Okay, zero trust is a fundamental strategic shift. Assume breach, verify continuously. Got it. Now, what about tokenization? You mentioned it briefly. How does that compare to encryption? Are they interchangeable or different tools?
A really important distinction, and one that causes confusion sometimes. Tokenization versus encryption. They both achieve the goal of data obfuscation. They make sensitive data unusable to unauthorized parties, helping meet compliance rules like PCI DSS for payment cards, IPA, health info, GDPR, personal data. But they work very differently, have different strengths, and are not interchangeable. There are different tools, often used together.
Okay, different tools. How does encryption work again, quickly?
Encryption uses a mathematical algorithm and a key to transform plain text into ciphertext. To get the original data back, you must have the key to reverse the math. It scales well. One small key can decrypt huge amounts of data. It works for structured data, like a credit card number, and unstructured data, like a whole document or image. It's good for sharing data with trusted third parties. You give them the key, they can decrypt. There are versions that try to keep the original data format preserving encryption, but sometimes that involves security trade-offs. And the key point: the original data, even though encrypted, still technically leaves your control when you send the ciphertext somewhere.
Okay, math, keys, scales well, data leaves encrypted. How is tokenization different?
Tokenization works completely differently. There's no mathematical relationship between the original data and the token. Instead, when sensitive data comes in, say a credit card number, the tokenization system generates a random, meaningless string of characters, the token. It then securely stores the mapping between the original sensitive data and this random token in a special, highly secured database called a token vault.
So the token itself doesn't contain the original data in any scrambled form.
Correct. It's just a random reference pointer. To get the original data back, a process called detokenization, you need authorized access to that token vault to look up the mapping. Scaling can be more complex because that vault needs to be fast, secure, and can grow very large. Tokenization is primarily used for structured data fields, things like credit card numbers, social security numbers, maybe bank account numbers, specific PII fields, not usually for large blocks of unstructured text or files. Sharing tokenized data is harder because the third party would need access to your token vault, which you generally don't want to give. A big advantage: tokens can easily be generated to match the format of the original data. You sample a 16-digit token that looks like a credit card number without weakening the security at all, because there's no math involved. And the most crucial difference for compliance: The original sensitive data never leaves your secure environment, the token vault. Only the meaningless token travels through less secure systems or gets stored in less secure databases.
Ah, that's huge for things like PCI DSS, right? Reducing the scope of where sensitive data lives.
Exactly. Tokenization is extremely common in payment processing precisely for that reason. By replacing real card numbers with tokens in most systems, organizations drastically reduce the number of systems that fall under the strict PCI DSS rules. It simplifies compliance enormously. It's also increasingly used for other PII for similar reasons, especially where legacy systems expect data in a certain format. So, use cases. Tokenization shines for structured fields like payment data or PII, where you want to remove the original data from systems entirely. Encryption is better for unstructured data, or when you need to securely exchange data with partners who need to decrypt it. Often you'll see both used in the same organization for different purposes, a layered approach.
That's a super helpful clarification. Two
Yeah.
powerful tools, different jobs, often complementary. Okay, we've covered a ton of ground. So pulling it all together, what does this mean for our listeners, whether they're building systems, managing data day to day, or just trying to make sense of this complex security landscape? What are the practical steps, the overarching principles that any organization should be thinking about?
Right, connecting all these threads. The big picture is clear. Data security isn't just an IT task anymore. It's a fundamental strategic imperative for any organization. It requires a proactive, holistic view. And yes, there are definitely some universal best practices that apply across the board, regardless of size or industry, things that can significantly move the needle on security posture. First, and maybe most importantly, cultivate a mindset of being proactive versus reactive.
Don't wait for the fire alarm to go off before buying fire extinguishers.
Exactly. Don't wait for a breach. Implement security measures designed to find your sensitive data, understand the risks to it, and protect it before something bad happens. That proactive stance is foundational. Build the strong walls before the storm. Second, ensure you have robust network controls. Seems basic, but still critical. Use modern firewalls, network segmentation, network access control, NAC solutions. Secure the pathways data travels on. It's digital border control. Third, and this is often underappreciated, implement systematic data classification.
Knowing what data you have and how sensitive it is.
Precisely. You can't protect what you don't know you have or don't know is sensitive. Categorize your data, customer info, IP, financial records, regulated data. Then you can apply the appropriate level of protection based on that sensitivity, whether it's at rest, in transit, or in use. Tools like Azure Information Protection are great examples of enabling this classify, label, and apply persistent protection. Fourth, develop software agility. This sounds operational, but it's crucial for security.
Being able to update software quickly.
Yes, you need the ability to rapidly deploy updated versions of tools, SDKs, applications, operating systems, third-party components. Why? Vulnerability management. Patching known flaws quickly is critical, and adopting new security features like the PQC updates we discussed requires this agility. If you can't update efficiently, you can't stay secure. Fifth, push to adopt modern protocols. Specifically, make a concerted effort to get your organization onto TLS 1.3 everywhere possible.
You mentioned that for PQC compatibility.
Yes, it's essential for PQC, but TLS 1.3 also offers significant security and performance improvements over older versions like 1.0, 1.1, even 1.2. Get off the old stuff. It's like upgrading from rusty pipes to modern, secure plumbing. Sixth, enforce the use of secure management workstations or privileged access workstations, PODWs. We talked about this with Azure. The admin or developer endpoint is a prime target. Using dedicated, hardened machines for sensitive tasks significantly reduces the risk of credential theft or session hijacking originating from a compromised workstation. Also, enforce security policies on all devices accessing data. And finally, if you're using cloud providers, which most organizations are, perform careful cloud vendor evaluation and understand the shared responsibility model. While providers like AWS, Azure, and Google Cloud offer incredibly robust security of their cloud infrastructure.
You are still responsible for security in the cloud.
Exactly. Understand what they secure, the physical data centers, the core network, the hypervisors, and what you must secure. Your data, your applications, your configurations, your access controls, your operating systems. Ask the right questions. Who can access my data? How is it encrypted by default? What key management options do I have? What are the backup procedures? Don't just assume the cloud provider handles everything. Your active participation is vital.
That shared responsibility model really is key. The cloud provider gives you secure building blocks, but you still have to build your house securely using them.
That's a perfect analogy. They secure the foundation and the building structure, but you're responsible for locking your doors and windows, managing who has keys, and securing what's inside your apartment.
This deep dive has really underscored just how intricate, how layered, but also how absolutely critical data security is today. From grasping those three states data at rest, in transit, and the crucial in-use state addressed by confidential computing, to exploring the proactive steps the major cloud players like AWS, Azure, and Google are taking, especially with things like post-quantum cryptography, it's clear this is a constantly moving target. And seeing how frameworks like Zero Trust are fundamentally changing the security mindset alongside specialized tools like tokenization, well, it shows we're developing more sophisticated defenses all the time. It really leaves you wondering, though, as data just keeps exploding in volume and complexity, maybe even moving into weird new quantum states or forms we haven't conceived of, how will our protection strategies have to evolve beyond encryption? What comes next? That's definitely something to ponder. Before we wrap up, a huge thank you once again to our sponsor, StoneFly. And speaking of robust solutions, especially for that data at rest security we discussed, you really should check out an incredible offer StoneFly has right now.
They're offering 100 terabyte immutable and air-gapped SSO NAS. That's network-attached storage for just $8,995. Think about that. 100 terabytes of secure, resilient storage. It's designed specifically to protect your critical data from threats like ransomware, using advanced immutability, meaning data can't be changed or deleted once written, and air-gapping features, providing that extra layer of physical or logical isolation. Plus, single sign-on for streamlined access. It's a really powerful package for securing backups and archives. For more details on this 100 TB offer and StoneFly's complete range of enterprise storage, backup, disaster recovery, and security solutions, head over to stonefly.com. That's STONEFLY.com. Stay safe, stay secure, stay well informed, and we'll catch you on the next deep dive.